University Research Fellow at the Imperial College London in the UK. And just a reminder for everyone, if you have any question that you would like to ask, feel free to just interrupt, but you can also leave on the chat, and Carolina and myself will monitor and could ask the questions on your behalf. So about James, so James' expertise is in pretty much all the physics that is relevant in the atmospheres of exoplanets, as well as accretion disks. And he has made several major breakthroughs in our field, including the prediction of the radius gap in exoplanetary data. And for those of you who are not in exoplanets, let me just say that that is a really rare feat in our field ever since the launch of Kepler. We have a lot of post-diction, but not so much prediction. So that was a really great piece of work. So about the academic background, so James completed his bachelor's, master's, and PhD at the University of Cambridge. Then he actually joined the Canadian community when he was a CETA fellow in Toronto for his first postdoctoral fellowship. And I believe we actually overlapped there when I was an undergrad student. Yeah, so we go way back. And he then moved on to the Institute of Advanced Study as a Hubble Fellow. And then in 2017, he decided to move back to the UK to the Imperial College London, where he holds the current lecturer position and the fellow position, which is equivalent to basically a tenured professor in North America. And I would like to add that ever since I started to study exoplanets as a grad student, I've been reading and referring to a large body of James's work, and I still continue to do so, as well as many of my students. So it is a distinct pleasure for me to host and introduce James. So without further ado, please take it away.
Thank you very much. Thank you for the wonderful and very kind introduction, Eve. It is a pleasure to be able to come to you and talk today, and also thank you for all moving the seminar. It does. Hopefully, it will benefit both of us because you'll get a better seminar because I'll be less tired. So I'm going to talk about sort of one thread of my research, and this has been heavily involved with a collaborator of mine, Richard Booth, who's a postdoc now at Imperial, and that's trying to understand sort of and tracing back the building blocks of planet formation through the protoplanetary disks. So these are the planet forming environments. And the reason we think this is important is because we think planets form in disks around young stars. So when I was starting out, sort of people like to show pictures like this in their talks, how are stars born. So you start from a cloud collapse, and the fact that cloud has some angular momentum means that when it collapses down, it can't collapse all the way into a point. You're left over with some residual material that is orbiting the central mass, and you have a disk. And in those disks, perhaps planets form, and then eventually the disk disperses, and you end up with a mature system. And now we're sort of, I like this plot because it says scenario largely drawn from indirect tracers, which is a good metaphor for how much of traditional astrophysics is done. But we're in the era where we can actually observe all these things. So this is, we can take a picture of a star-forming cloud. This is a star-forming region. You can see the color coding here is the velocity blue shifted or red shifted with respect to us. So you can see that this large cloud has some residual rotation, right, that leads to the formation of a disk when it collapses in on itself. So this is a nice image of a protoplanetary disk here with an outflow. And we're even now doing a bit better, that we can take even high resolution images of these disks and actually see forming planets inside them. So this is the famous PDF-70 system, where we have a dust and gas disk we can image with the ALMA telescope. And in this cavity in the disk, we actually see two planets here, PDF-70b and PDF-70c. And we detect the planets in the continuum, but we also detect them in H-alpha emission, which is a shock tracer. So we're actually seeing material actively falling onto the protoplanetary environment and accreting onto the planet. So we are truly seeing planets growing in action today. And if we look a bit later, we can see mature planetary systems, and we can even see them orbiting their own star. So this sort of picture that planets form in disks is pretty well established now. And while the sort of parts of this are sort of state of the art in the observational perspective, particularly this part of actually seeing planets form, the outcome of planet formation is particularly well established now, thanks to exoplanet surveys. So this is the planet mass against orbital period, or planet radius against orbital period. As you can imagine, we're biased towards large planets close to their stars, but we've done incredibly well in detecting thousands and thousands of exoplanets. So there are a couple of things you take away from this diagram, right? Maybe our observational techniques have really not probed down to what are solar system analogs, but we have a lot of scatter in this diagram and a lot of diversity. And one of the goals, one of the things that I'm particularly interested in, this is sort of what drew me specifically to working in the exoplanet field, is that this is a wonderful theoretical problem. And Eve highlighted the ability of theorists to do well and predict things. So I like to show this fun picture here, which is the sort of outcome of planet formation models we had pre-launch of Kepler. So this is the planet mass on the y-axis as a function of semi-major axes. And this basically is a planet population synthesis model. So what this means is people took what they thought was the best description of how planets form in disks and evolve around young stars, and then cranked the computer handle and asked what the outcome was. And the thing to remember, right, is that sort of 13 years ago when this was done, the outcome of our solar system was really one of the building blocks of what we thought planetary systems looked like. And we had a good number of hot Jupiters at that point. So you can see that these models quite nicely produced a population of terrestrial planets. In the inner solar system, inner regions, they formed a population of ice giants at larger radii. And then sort of at intermediate semi-major axis, you form giant planets, some of which were able to migrate in through their interactions with the protoplanetary disk and form hot Jupiters. And the fascinating thing is that this prediction does spectacularly badly in predicting the exoplanet population. So in fact, we now know the most common type of exoplanet we've detected are these sort of close-in, moderately sized planets between masses between 1 and 20 Earth masses, or radii between 1 and 4 Earth radii. They are by far the most common and most abundant type of exoplanet we've detected to date. Almost most Sunlike stars host one of these, so it's not just that we're able to detect a rare population. These are a dominant outcome of planet formation. Yet our planet formation models of the previous decade failed to account for these. Now, there's obviously been a lot of theoretical work in the last decade trying to reconcile this, and we have some good ideas about how they may form, and Eve's been one of the pioneers of that area. But this is an observationally led field, right? And maybe observations can provide some additional clues. So all exoplanet detection and survey methods are really giving us a bulk properties. So we can measure the planet's radius through an exoplanet transit, or we can measure the planet's mass through radial velocity follow-up or transit timing variations. And they give you something about the bulk density of the planet, and then you can roughly work out what that planet might be made of in terms of sort of bulk quantities, right? How much iron do these planets have? How much rock do these planets have? How much hydrogen, helium do these planets have? But we would like to do a bit better. And the next frontier of exoplanet science is really studying their atmospheres in more detail so that we can get a better handle on the compositions of these atmospheres. And this detection of their composition happens through transmission spectroscopy. So instead of just doing a a transit measurement where you're looking for the dip in brightness as the planet transits in front of its host star over some broad range of wavelengths, what you can do is you can do this kind of experiment as a function of wavelength. And different molecules and different species in a planet's atmosphere at different wavelengths will absorb more or less strongly and imply that the planet has a larger or smaller radius. And by measuring this, what's called transmission spectroscopy, or essentially the planet's size as a function of wavelength, with an instrument like the upcoming NASA James Webb mission, then you can compare that to models and say something about the chemical constituents of the planet's atmosphere, and maybe that will give us a better clue as to what and where the planet and how the planet formed and accreted its constituent material. So sort of one of the goals maybe of the next decade or next 2 decades of the exoplanet field is to take our exoplanet population that we have and do more detailed studies of their atmospheres. So trying to measure what the chemical compositions of their atmospheres are, and then mapping that back to the planet-forming environments, these protoplanetary disks, and trying to say, these exoplanets have this type of composition. Maybe that implies they formed under these conditions in the protoplanetary disk. And the reason why this can work so well is these protoplanetary disks cover a large scale in both size and temperature. So this is just a nice schematic here on the right-hand side, showing that sort of the inner regions of the disks are quite hot. So almost even dust particles are completely vaporized in the inner regions of these protoplanetary disks. So this is where we actually find a lot of planets. But as you move out, these disks are heated primarily by the central star. So the further away you get from the central star, the colder the disk gets. And you can actually get ices. You can condense volatiles like water, carbon monoxide into the solid phase and into ices. And given some of these planets contain gas and some contain solids, the chemical makeup of the various gases and gas species and solid species should allow you to map into the chemical constituents of the planet's atmosphere and learn something about that. And it's particularly what are called these snow lines. These are the transition radii in disks, where inside the disk you're hot enough for a certain species, like water, for example, to be in the vapor phase, and outside this snow line you're cold enough for this species to be in the solid phase. So water outside this snow line condenses into ice phase. So this means that the chemical makeup of both the gas and solid varies as a function of radius. And there was this very nice piece of work 10 years ago now, led by Karen Oberg, sort of pointing out that this is an excellent way to learn about exoplanetary origins from their composition. And one of the key diagnostics was perhaps the carbon to oxygen ratio. And the reason why the C to O ratio, as it's called, or carbon to oxygen ratio, might be such a key diagnostic is that many of these important ice lines in these protoplanetary disks, so the water ice line, the carbon dioxide ice line, and the carbon monoxide ice line, are where large amounts of elements change their phase from either being in the solid phase or the vapor phase. So this diagram here shows a sort of how the carbon to oxygen ratio of the gas might evolve and the carbon to oxygen ratio of the solids, and this is sort of what solar composition looks like. Now, if you read this paper, this is sort of a very schematic paper, and it's sort of putting this idea together, right, rather than suggesting that this picture here, as drawn on the right, is the answer. So the goal of this kind of stuff on the left here is to make measurements of the planet's atmospheres, measure their spectra with JWST, determine how much water they have, how much carbon monoxide they have, how much carbon dioxide they have. So this is sort of a plot showing, wow, JWST is going to be so much better than Hubble. We'll be able to precisely measure the carbon to oxygen ratio of this exoplanet, and then I can just map that value to a position in the disk and say where it formed. But what I'm going to highlight throughout this talk is I actually think the technical challenge of this field, right, it is not on the left-hand side. I think the challenge of this field is actually on the right-hand side, is actually computing these models and saying something about where, or using these observations to say something about where these planets form. And like all things in science, I suspect it's going to happen in hand, that the observations are going to give us some answer about what the distribution of the chemical constituents of planets' atmospheres are, and that will give us some clues as to how we think they may form, and our models can then sort of iterate back and forth. And just as a sort of a highlighted example of sort of the problems we're facing in this field here is that when we take our best models for the chemical evolution of protoplanetary disks, we can try and use observations of carbon monoxide from the disks to estimate the disk mass. Right? So we take models of protoplanetary disks with disk chemistry in there. We predict how much carbon monoxide there is and how much carbon monoxide is in the gas phase, and then we use that to predict a line flux, which we then compare to the observed line flux, and that tells us something about the gas mass. So this is a very common way of estimating gas masses. But carbon monoxide is not a major component of the disk. So molecular hydrogen is a major component of this, which we can't actually observe. But we can observe hydrogen deuteride, so a hydrogen atom and an isotope of hydrogen. And this gives us a much better and easier way of precisely measuring the disk mass. And I'm not going to lie that it's an easy measurement. It's also a technically challenging measurement. But I think the fact that these two measurements, the disk masses derived from hydrogen deuteride and derived from carbon dioxide, can differ by up to a factor of 100 is pointing to the challenge we have in the protoplanetary disk community for understanding the chemical evolution of these disks. And I want to highlight ALMA is making incredible advances in terms of this field. So ALMA is a reasonably new sub-millimeter telescope in Chile. It's increased our sensitivity to study many things in the sub-millimeter, including protoplanetary disks, by at least an order of magnitude, both in sensitivity and resolution. So we have these stunning pictures of disk structures that are telling us something about planet formation. So this is from the D-Sharp survey. But in the last sort of couple of months, we've had the first results from the MAP survey, which is where they took 5 of these disks here and they observed them in many different molecular line transitions. So you can see each panel here is the same disk, but in different tracers and different molecular species, they look very different. So this is telling us something about the chemical evolution of these planet-forming environments. So to the modeling and to the theory, and what progress have we made and what can we make? And the real challenge of why this is not an easy thing to do is that when your species are in a solid phase compared to in the vapor phase, they can move at very, very different speeds. So when a species is mixed within the bulk of the hydrogen gas, it slowly accretes through the accretion disk onto the star on million-year timescales. But now imagine you've put that species into the solid phase. So you now have a solid particle like dust, a dust particle. The typical structure for a protoplanetary disk, because it's heated by the central star, is to be hot near the central star and cold further away. Models of disks to allow you to steadily accrete onto the star tend to have surface density increasing towards the star. And this is simply because you want to conserve mass flux, but the area in the disk, each annulus is getting smaller and smaller and smaller, so you need more stuff locally to have higher, to match the same accretion rate. So this means that pressure is decreasing outwards, right? So if you want to be in radial force balance, in the gas, you want your pressure plus gravity to balance your centrifugal force. So this means the gas doesn't quite orbit at the Keplerian velocity. Now, the same thing happens to the dust particles, and you will often hear people say, dust doesn't feel the pressure gradient. That's not quite a true statement. Of course, the dust particle feels the pressure gradient. The difference here is the dust particle has, for the same volume of gas, has a mass that is at least 20 orders of magnitude higher. So the acceleration the dust particle feels from the same force is completely negligible. So the correction to the orbital velocity of the dust particle due to this pressure gradient is completely negligible. So it wants to orbit at the Keplerian orbit. So the gas is going slower than Keplerian and the dust is going roughly at the Keplerian. So this is like riding your bike into the wind. The wind wants to slow you down. And if you slow yourself down, you lose angular momentum and you transport your spin upwards. And this process is fairly efficient. So if we look at a simple model of this is a gas in blue, dust in orange. We'll start off with a disk model where we fully mix everything at the start. And what happens is that the dust particles drift in and we deplete the dust close to the star or in the middle of the disk rapidly, and it piles up in the inner region. So the outcome tends to be that perhaps you enhance the solids in the inner disk relative to the gas compared to what we started off with, and you deplete the outer disk relative to the gas. So perhaps enhancing the inner disk in solids might be useful for planet formation, but I'm not going to talk about that today. But the key is that solid particles can move relative to the gas. And perhaps we have some observational evidence for this, which is where we go look at a disk. This is TW Hydra. It's one of our closest protoplanetary disks. And we look at it in the solid phase. We see quite a nice compact disk. And you look at it in the gas phase, you see it's much larger. So one of the interpretations is that the solid particles have drifted in with respect to the gas. There's more subtleties to this that you can ask me about. It's still it's not entirely settled as to whether this is convincing observational evidence for this process, but it's at least in the right direction. So if we put this all together into a schematic picture, in the outer disk we have solids that contain ices and refractories. And what refractories mean is basically solid particles that have melting points that are so high, they basically stay in the solid phase until you get ridiculously close to the star, until you get to within a few stellar radii where you can be heated up and to several thousand Kelvin and melted. So you can think of refractories as close to like metals and rocks. Whereas in the outer disk, we have volatiles and ices. So if we have the ices in the solid phase, they're going to drift with respect to the gas. They're going to cross one of these snow lines where you can liberate your ices and turn them into gas phase. So in the case here, in this picture, we've taken our water ice, we've drifted it in and released water vapor into the inner disk. Now, because these gas disks are accretion disks are turbulent. So there can be some backward transport of material due to turbulence outwards. So either you can transport some water vapor back across the snow line, or you can transport some of these refractories further out into the disk. So what I'm going to do is I'm not going to give you the answer to this entire problem because I don't think a convincing answer to the chemical evolution of an entire disk exists. What I am going to do is I'm going to talk about a few specific things that I think are interesting that are giving clues as to what might be going on. And I'm going to start off with the simplest thing, which is these refractory particles, i.e. sort of things that stay in solid phase in most of the disk, because this simplifies a lot of the processes we're worrying about, because we can kind of ignore chemistry and phase changes. And I'm going to try and link this to planet formation. And I'm going to try and link this to planet formation somewhere really close to home, right, in the solar system. And one of the intriguing things about the sun being very close by, we can take incredibly precise measurements of the sun's chemical makeup, is that the sun, when compared to other sun-like stars, so these are solar twins, so these basically the closest stars that have almost precisely the same mass, age, and radius as the sun, they appear to be depleted in, or the sun appears to be depleted in refractory elements. So what is plotted here is the elemental abundances in the sun compared to the average of all these sun-like stars. Plotted as a function of condensation temperature. And condensation temperature is essentially melting point, but it's melting point at a specific pressure with a specific composition. So you shouldn't read too much into the ordering of these specific elements, rather the groupings in terms of high condensation temperature means refractory, very hard to vaporize, so something like the constituents of rock. So this measurement is for the surface of the sun. So the surface of the sun is convective and contains about 2% of the mass of the sun. So perhaps what has happened is we've depleted this surface layer of the sun with these refractory materials. And perhaps this had something to do with planet formation that happened in our solar system that didn't happen in other sun-like stars. This was a sort of a pioneering observation. The number of solar twins is 9 in this observation, so it's sun compared to 9 nearby stars. But the opening up of large-scale astronomy and spectroscopy of large numbers of stars have allowed this to be done for a very large number of stars now. So this is a plot from Megan Bedell's work that compares the sun to almost 100 nearby solar twins. And it shows basically the same trend. You can argue whether you see a specific line with condensation temperature, whether there's a specific trend, or whether you're just seeing a trend in the volatiles and the refractories, which is what I'm going to talk about specifically. And I think in the new data, it's more convincing that it's sort of maybe sort of 2 bulk populations, that you have a bulk population of volatile elements that look normal, and then refractories that look slightly depleted. So the idea was, well, what's interesting about the sun? Well, the sun has terrestrial planets. So perhaps the answer was that most other sun-like stars, all these dust particles that contain these refractory elements, drifted through the disk from the outer region and drifted all the way onto the star. And in the sun, these solid particles, they drifted into the inner disk and they gave rise to our terrestrial planetary system. There's sort of a particular, there's two problems with this. There's one theoretical problem, which is that there appears to be a timescale mismatch, which is that what we're measuring is the amount of depletion in the surface layers of the sun. So this thin convective layer. But if we wind back the clock and ask how deep was this convective layer when the sun was born, it was considerably deeper. So instead of stopping sort of 2 or 3 Earth masses of material accreting onto the surface of the sun, the amount of mass you now need to stop accreting into the bulk of the sun is much higher. And we have to do this early because most protoplanetary disks are dispersed by 10 million years. So even at 10 million years, the convective zone size of the sun still makes up a significant fraction of its total mass. The second problem is now we can we can go back and answer this hypothesis from the exoplanet surveys. Did most other sun-like stars not form close-in terrestrial planets? Well, the answer is exactly the opposite. In fact, most close-in sun-like stars did form lots of planets, and in most cases, much more massive than in the solar system. So, if you do a statistical study based on the exoplanet population, what you actually find is that if you believe in this scenario where refractories in their solids are drifting in from the outer disk, some of which are turning into planets and some of which are accreting onto the star, then based on our statistics from the exoplanets, the sun should actually not be depleted in refractories, but actually enhanced, because we have a very, very low mass in a planetary system, and most other stars have a much more massive interplanetary system. So in most other stars, more material got sucked up into planets than would have drifted onto the star compared to the sun. So in this scenario, the sun actually ends up as a star that should be enhanced in volatiles, and the kind of depletion levels we see in the sun should be an extremely rare event, something like 1 part in 1,000. Whereas the statistics from the other surveys are showing it's something like a 5 to 10% effect. So what else could be going on? Well, one way to stop this happening is to stop these refractories accreting all the way onto the star. And one obvious way to do that is to stop this radial drift through the disk. And one way to do that is just to change the direction of the pressure gradient. So instead of having the particles drag inwards, if I change the direction of my pressure gradient, I can make the particles move inwards towards this pressure maxima and outwards towards this pressure maxima, piling material up in a gap in a protoplanetary disk. And we have good observational evidence that this actually happens. So this is, again, is a nice image of that PDS-70 disk that has forming planets in this cavity. And what we see is a ring of dust that's perhaps being trapped by the forming planets. The forming planets carve a gap in their gas disk, they reverse the standard pressure gradient, and they trap solid material. You can actually do a similar style of analysis to white dwarf debris disks with more massive stars, so Herbic stars. Herbic stars actually have a very thin radiative zone. So any material that you drop onto them is going to rapidly sink through the atmosphere. So any chemical anomalies you see in the surface layers of these Herbic stars tell you about what has just accreted onto the star. And what we find is that if you look at these transition disks, so these open symbols here, compared to the normal disks, so these are disks with, these are disks with holes, perhaps caused by forming planets, and these disks are without holes, they're just normal disks that ascend all the way to the star. We find that when we look at the volatile elements, the abundances in the surfaces of these Herbic stars are identical, but when we look at the refractory elements, we find that the transition disks, the disks with these cavities that are trapping a lot of dust at large radii in their disk, are quite depleted. So does this work for the sun? And right, we have a giant planet in our solar system, we have Jupiter. So this is a sort of a simple model that Richard and I ran, where we insert a forming planet into the protoplanetary disk. It forms one of these pressure traps that is allowed to trap large amounts of solid particles outside its orbit. And we can actually trap sufficient particles outside its orbit and prevent them accreting on the star to actually explain this refractory depletion. So I'll just show the outcomes of these simulations. So this is the metallicity of the surface of a sun-like star, our sun, with a giant planet, compared to a model that didn't form a giant planet. And we find that this scenario can nicely explain the kind of level of depletion we see in the solar system. So at the broad brush level, we have hints that the formation of planets can affect the compositional evolution of the disk, and that compositional evolution of the disk can imprint itself on the chemical composition of the stars. So that's a nice picture, but it's relatively simple, and it doesn't quite get to the question I posed right at the start of this talk, which was more about how does the exact chemical composition of the disks evolve, and how might we link that back to atmospheric composition and planet formation. And that really we need to start worrying about these more volatile species, so particularly this wonderful carbon and oxygen, and what happens at snow lines.
James, before you go on, can I ask you a question?
Sure.
So do I understand correctly that the point is that to carve out a gap, perhaps by planet, like Jupiter-sized planet, you just trap the refractory materials on the outside and deplete the refractory materials on the inside?
Correct.
Is it potentially problematic with the observational hint that there's a correlation between the outer gas giant and inner super Earths?
Yes.
Okay.
Yeah. So if the well, yes and no, right? So if you believe that the reservoir for forming the inner super Earth is the material that would have otherwise drifted in, right, that's got blocked, then it's problematic. If it's more of a correlation that planets that or disks that are proposed to form planets will just form planets at all radii, right, then it's less of a problem.
Okay.
Great. So on to the complications of the volatiles. So let's zoom in and look at these snow lines in a bit more detail, right? So these snow lines, as we discussed, were positions where the refractory component, the volatile component, when it crosses the snow line, is able to turn into the vapor phase. And because these disks are turbulent, what you find is you transport some of that vapor back across the snow line, and it condenses into the solid phase again. So not only do you get material rapidly crossing the snow line, it also diffuses back. So you get an enhancement of solids just behind or just at the snow line. So this is what some nice models of Richard Booth is showing, that these here are rough positions of the snow lines, and you see this effect quite nicely, that solids are drifting in, they're diffusing back across the snow lines, and you're getting this bump here exterior to the snow lines. So this kind of complicates this simple picture here, where the C/O ratio can be just mapped directly to the positions of the snow line in a static disk, right? And this was just a calculation of a static disk, a schematic calculation for a static disk. So this drift is going to give us enhancements close to these snow lines. So let's just look at some results without this drift, right? So this is exactly what is kind of being shown in these calculations. This is just the evolution due to chemistry from some of Richard's latest calculations, that you do get this nice step function in the CO. So even in a time evolving disk, so the previous one was an equilibrium disk, this time evolving does give you this nice step case. However, if we switch on the drift, we get dramatically different results, right? And I want to highlight the range of the y-axis here, going from 0.2 to 1.4, right? And now if I switch on the drift, immediately everything looks different, but also the y-axis now is ranging from 0 to 7 here. And I'm getting these huge pileups near these snow lines, very rapid changes in the C/O ratio at these snow lines positions. And this simply is due to the fact that we have the solid particles racing into the snow lines. They diffuse and melt just inside, and we transport that vapor back, which forms new solids, and you get a nice massive enhancement at the snow line. And this gives these enormous spikes in the C/O ratio at these various snow lines, or very rapid changes. And you can also see it's a strong function of time. And if you ignore chemistry, then you get a dramatically different answer. So it's a beautifully coupled problem, that the drift affects the chemical composition, and it's happening on a time scale which is short compared to the time scale to reach chemical equilibrium. So the sort of time evolving chemistry really matters as well here. So it's becoming a murkier picture as to how we might do this, but it's nice and rich. And I'm gonna sort of, in the last 5 to 10 minutes of the talk, I'm going to also try and make this even worse for you and say it's an even more complicated problem, but a delightfully fun one. And that's because every calculation that I've shown you and every calculation I've done so far is people just lay down the temperature structure of their protoplanetary disk. They just say, the temperature structure of my protoplanetary disk is this. But as you hopefully know, the protoplanetary disks are heated by the central star. The absorption of stellar light by is done by the solid particles in the disk predominantly, and therefore the distribution of solids in the disk should affect the temperature distribution of the disk, and obviously the solid distribution is dependent on the temperature distribution. So it's wonderfully coupled. So disk temperature depends on the distribution of solids, and the distribution of solids at these snow lines depends on temperature. So let's just think about exactly what sets the temperature of the disk, right? So they're heated by the central star. They're not radially optically thin, so the stellar light does not penetrate all the way through the midplane of the disk. Rather, it heats the surface layers of the disk, and then the surface layers heats the center of the disk. So let's zoom in a little bit more and think about this, right? So we have our star here, and now I have a cross section of the disk where I have particles throughout my disk. And what happens is my starlight comes in, it heats the surface layers of the disk, and the disk cools both vertically, emitting radiation to space, and that's the radiation, some of which we see. It ends up hot because of the emissivity ratio due to the small particles, that they're receiving short wavelength light, but emitting long wavelength light, so they end up hotter than you would naturally get from the black body approximation. But some of this radiation is sent towards the midplane, which heats the midplane. Obviously, you get roughly half the radiation that the surface layers absorb from the star, because you lose half the space and you spend half down. So the disk plane is going to end up a bit colder than the surface layers, and it's going to cool through even longer wavelength photons. So why is this incredibly important? Well, this is important because the opacity, or the preponderance of this of different portions of the disk to absorb different wavelengths of light strongly depends on the temperature of the radiation field. So the radiation that's heating the midplane is hotter or shorter wavelength than the radiation which is cooling the midplane. And because opacity increases with the radiation of the temperature, the optical depth to the heating photons here is higher than the optical depth to the cooling photons. So this means that these heating photons are more likely to be absorbed in the midplane of these disks than it is for these cooling photons to escape. So how might this affect the snow line? So let's imagine 3 different scenarios, right? Everything's optically thick to both cooling and heating radiation. So basically, I just have a slab in the middle of the disk. All the radiation that gets sent down by the surface layers gets absorbed, So this means that the heating rate doesn't really depend on how much material is there, right? I could double it and still all the radiation would be absorbed. The cooling rate also doesn't depend on density, right? It's just a slab. It behaves like a black body. So this means if I change the amount of solids, it's not going to change my heating and cooling rate, so I'm not going to change my temperature. Let's go to the fully optically thin case. In the fully optically thin case, the heating rate depends on how much material I have linearly, right? How much of that incoming radiation can I emit? And the cooling rate also depends on linear on this amount of density, right? How much material do I have to emit itself? So this means if I change my amount of density by the same, I change my density by some factor, I change my heating rate and cooling rate by the same factor, and the temperature remains unchanged. But we have this intermediate stage because the optical depth to the incoming radiation is different to the optical depth to the outgoing radiation. So if we're marginally optically thick, so we're optically thick to all the incoming radiation, basically all the incoming radiation that's sent down from the surface layers, we always absorb it. So the heating rate is independent of density, but the cooling rate is optically thin. It depends on still how much density we have here. So you can imagine a scenario where I slightly reduce my amount of solids by melting some of my volatiles. If I melt some of my volatiles, because I'm optically thick to the incoming radiation, my heating rate stays the same. So I still have the same amount, I still absorb the same amount of irradiation from the top and the bottom. But my cooling rate is reduced, right? Because I have less material. So if my heating rate has stayed the same and my cooling rate is reduced, this means my temperature is heated up, but if I've got hotter, I'm going to melt more solids, right? And I'm just going to enter a runaway. I could do it the opposite way. I could increase my amount of solids, I increase my cooling rate, I cool down, and I'm going to condense more solids out of the vapor phase. So this means that snow lines are sort of thermally unstable, right? You can't have a fixed amount of solids at a fixed temperature if you're at intermediate optical depths, because either you'll either go through a phase where you heat everything up and you melt it, or you'll go through a phase where you cool everything down and you condense it. So I'll skip this and point out this is really important, right? Because the solids and the vapor move at different phases through the disk. So I can imagine I've gone through one of these phases where I condense everything down, I turn it into solids, and then it's going to rapidly drift through the disk. It's going to empty out this region of material, and it's going to take a long time to replace it with any other vapor because that moves at a much slower rate. So this can be characterized as a limit cycle. So you can imagine that you're feeding the disk from the outside with some flux of volatiles, and you get to a radius where the snow line is sort of thermally unstable. So either you have your snow line in the vapor phase, the accretion rate of solids through that region is really slow. You build up the amount of volatiles in that region, and it slowly cools the disk till suddenly you get cold enough that you can transfer yourself and melt, and condense everything. And then you dramatically cool. And then you start moving very rapidly, all your volatiles drift back out, and you keep going round and round and round in this cycle. And if you know anything about sort of classic thermal instabilities in more high energy disks, this is almost exactly the same analogy. It behaves very similar. But this is all very schematic. So let's pick a real simulation and let's do a real simulation. So what we're going to do is just take a model for how we heat and cool the disk, and we're going to couple it to a model for the chemistry and see what happens. Right, so this is a plot of the various surface densities in the disk as a function of radius. We have our carbon monoxide vapor here shown in dotted blue lines. We have our total solids here shown in orange. And then we have solids which don't include the CO, which can change phase at this snow line, which I have here. Right? So this is the position of the CO snow. And I'm going to let this simulation go, and you find that the snow line never actually settles down to a single position. Right, and this, the snow line is rapidly moving in and out through the disk over large radii range, tens of AU, dramatically changing the carbon to oxygen ratio in the gas and the dust phase. So you can imagine that if you're a planet sitting here forming, the carbon to oxygen ratio of the gas and solids you're accreting is going to dramatically change. So this is very exciting. It complicates the picture even more, but it makes it fun. What makes it even more fun is while this process is happening, the way I describe the star heating the disk is that the star heats the surface layers. Right? But if I suddenly put in a snow line that has a huge change in solid surface density, I'm going to block the starlight from further out. So this is kind of a video showing the positional height of the photosphere in the disk. And when you go through one of these bursts, you actually shadow the region behind it, and you can't heat this region before. So it's potentially that when you do that, you'll cool down behind that region and create another snow. So a nice hypothesis might be that not that we just get single snow lines of each species, that we're going to get multiple moving snow lines, which would make it even more complicated and even more fun. So thanks very much for listening, and thank you for moving your seminar forward. And I'll end there. So I personally think in this sort of mismatch between, or this matching, trying to match chemical compositions of exoplanet atmospheres to disk models, it's us on the disk side that are really letting the team down, and it's the protoplanetary disk models that are going to be poorly understood, and we really need to make important strides before we can start talking about exoplanet origins. Perhaps one clue that we can look at is the refractory depletion in sun. I think it's quite clear now that it's not explained by the origin of the terrestrial planets, which was the original hypothesis, and perhaps by giant planet formation. We need to start thinking not chemistry in a passive sense, but in an active sense, and can actually control the dynamics of certain portions of the disk. So thanks very much. I'll stop there and I'll take your questions.
All right, thanks, James. I'll clap for everyone else. And questions? Bjorn?
Yes, yeah, very interesting, James. The last part in particular, when you talk about this dynamics, the dynamic role, the timescales that you showed, they were relatively short, right? So these cycles that you call them, they were of the order of 10,000 years or so?
Correct, yeah. The hidden thing about that is that the time scale is extremely sensitive to the diffusion process across the snow line, and that's set by the strength of the turbulent viscosity, right? Which I'm sure you know is incredibly poorly known, right, to many orders of magnitude. So I can make that time scale change by at least two orders of magnitude by changing, but it's still short compared to the rest of the disk processes.
Yeah, so that's what I was actually wondering, especially at these longer orbits, is the dynamical timescale of the disk, does that also matter? I mean, does your model consider that, or does your model kind of consider the disk locally static or something like this?
So it's built within the standard thin disk framework. So it assumes that the disk is in vertical hydrostatic equilibrium, but it doesn't assume that the disk is in thermal equilibrium. So we're dynamically calculating the temperatures. So it's just about okay for 10,000 year timescales for the disk to be in dynamical equilibrium. But we had to relax the assumption of thermal equilibrium because the timescales were just too fast. But I have a student working on this now, and we're going to actually do some simulations where the dynamics is more respected, I guess. The other the other curious thing, right, is that you have rapid changes of temperature that are propagating through the disk, and that should create hydrodynamic effects, which are not incorporated in the thin disk model.
Okay, very cool.
Nick?
Thanks, James. I learned a lot from your talk. That was great. So I'm a little bit, well, I don't know if I should be worried or happy. That it sounds like this carbon to oxygen ratio that a lot of people have been thinking about for a long time, by making it more complex, on the one hand, I got excited for a moment. I was like, hey, maybe we're going to find planets out there with truly outrageous C to O ratios. But then if like these ice lines are moving about and changing in time over a time scale comparable to the formation of a planet, maybe the central limit theorem tells us that all planets are going to have very boring C to O ratios at the end of the day. And so like, I mean, I understand that when you're using like ALMA observations, obviously you can actually try and constrain this, but is like, how are you leaning now? Are you more optimistic, or are you losing faith in like using C to O ratios of fully formed planets to tell us something about their origin?
I think I have strong opinion. I have a strong faith that kind of direct flow of information is not the way it's going to work, right? I think the flow of information is going to be in both ways, right? So if you guys come back and say to us, hey, all planets have the same C to O ratio and it's basically solar, right? That tells us something very interesting, right? If you come back and say, hey, hot Jupiters have a bimodal C to O ratio, right? That also tells us something super interesting. I think it's not a one-way street. You're gonna have to tell the disk modelers, right, this is what we found, right? And this links also to the dynamical architecture of these exoplanet systems. So this type of exoplanet system has this type of C to O ratio. Calibrating our models against ALMA observations is a must, an absolute must. And sort of even the simple levels we've been doing have failed quite badly. Right? There's this huge missing carbon problem in protoplanetary disks. There's a missing carbon problem in the solar system. Right? We don't know where all the carbon went in terms of the Earth. But I have strong hope that between us we'll get to the right answer. Right? It's just I think the way it's sometimes sold within the exoplanet community is, hey, we'll be able to work out where hot Jupiter was formed. It is not the way it's going to go. But I would hope that we do get some outrageous C to O ratios, right? So if snow lines are important sites of planet formation, right, then we are going to get some outrageous C to O ratios.
Michael?
Hi, James. Yeah, this kind of builds off of Nick's question, but like as an observational exoplanet astronomer, like kind of for the more the protoplanetary disk side of things, like what is the most important thing that I guess the observational astronomers, the observational exoplanet people can give you to really help with this problem? You're like, is it more C to O ratios? Is it volatile to refractory ratios? Like kind of what is, if you had to pick one or maybe two things are kind of most important for this, what would they be?
Yeah, so the sort of, I would encourage you to read Richard's 2019 paper, right, which was a nice piece of work where he just didn't look at the C to O ratio. He also looked at others, and he sort of was pointing out that nitrogen, which acts through the ammonia snowline, is a good sort of discriminator of what's going on, right? So that you could sort of really use that to perhaps piece together what pathway the disk went through, and really trying to place the planetary atmospheres in terms of not thinking about specific values of C2O, but sort of C2O to nitrogen regions of parameter space, and certain areas of the disk and certain planetary formation hypotheses, like pebble accretion versus planet tessile recreation tend to populate certain specific areas of that diagram. So I think it's moving slightly beyond C2O and looking at other tracers. So the reason why this comes up is that methane can affect the carbon chemistry in the CO2 and methane snowlines. So that's kind of the observational starting point, I think, from the exoplanet side, is thinking about more molecules.
Well, thanks.
Other questions? Can I just go back to this formation of Jupiter blocking material?
Sure, yeah.
So this isn't the first, I mean, that kind of idea has been brought up before. And I generally like the idea of saying that something about the bulk property of the disk may have something to do with whether you form planets or not. But like in the context of, regardless, you have to block out the refractory reservoir, I worry a bit about the relative timescales of everything within the disk. It seems like you have to time things like very precisely so that you can form the terrestrial like or super Earth, mini Neptune like planets on the inside, but still block out the material and have gas giants on the outside.
Yeah, so to make it work for the sun, we had to form Jupiter early, because it's not just that, because of the size of the convection zone, it's not sort of a few Earth masses of material you need to prevent accreting on. It's actually close to 100 Earth masses of material.
Mm-hmm.
So the way we got it to work was by having Jupiter form early. Now there's good circumstantial evidence from the meteorite record that probably happened.
Mm-hmm.
But if you form Jupiter a bit later, right, then that 100 Earth masses of material has already gone past the orbit of where you would have formed your giant planet. And then it's available for you to turn into super Earths. So I think the solar system problem is fine-tuned. But it's the solar system, right?
Mm-hmm.
I'm happy fine-tuning the solar system.
Mm-hmm.
It does make specific predictions, right? So the specific testable predictions. So the Megan Bedell's work also identified in her sample of 100 solar twins a handful of other depleted stars. So if this is the origin scenario, then once we're able to characterize the outer planetary systems of these stars more precisely with Gaia, probably, then we should get a good constraint, right, as to whether this is the origin scenario. The other cool way to do this is to look at binaries, right? So binaries that are wide enough separations that you don't think that they affected each other's planet formation, but close enough that you feel they've formed in the same molecular cloud or the same core, so they had potentially the same compositions. There's some nice work by Joanna Teskey that you may have seen that it kind of holds together with one or two exceptions. That in general, the companion of the binary that has a Jupiter mass planet, and in almost all cases that's a hot Jupiter, appears to be depleted in refractory slightly. For me, the big clue is those Herbics, right? Mm-hmm. That is a huge clue that this trapping does happen. But you have to do it early. If you don't do it early, then that 100 Earth masses go straight into the inner solar system, and you can form your super Earth.
Right, and when you say early, what's the Can you give me a number?
500,000 years, by
Okay.
500,000 years. By 500,000 years, you have to have established Jupiter's core.
Right. Okay.
So it's essentially set by the growth time in the outer disk for most of the mass.
Mm-hmm. Right. Okay. Sorry, you had more to add?
Yeah, I was going to say it's not a complete story, but it's the best one I think I know exists.
Mm-hmm. Cool. All right, other quick question? If not, James, you have meeting with the students in 5 minutes. And otherwise, let's thank James again for the excellent talk, and I'll clap for everyone else again. All right, have a good day, everyone.